Alright, in this video we study continuous functions, and continuous functions are, in a sense, well behaved and therefore easy to handle or analyze. And many of the functions we study in calculus are continuous. Okay, let's start. So let's give the definition of a continuous function. We say, suppose we have a function f of x defined on some interval I, and suppose point A is an element of this interval. Okay, so function is defined on some interval, and point A is within that interval. And we say f of x is continuous at A. This means, by definition, the limit of f of x as x goes to a is equal to f of a. Okay, by assumption this a is within the domain of this function, so this is defined. And this is just the limit of f of x as x goes to a, and if that limit is equal to the value of the function at that point, x of x equal to a, then we say this function is continuous at a. And we say f of x is continuous, is a continuous function. Okay, note that we are not specifying any specific point here. We just say f of x is a continuous function. So it means it is continuous at every point in its domain. Okay, so this means f of x is continuous at every x in the interval. Okay, this interval is the domain of the function. So if f of x is continuous everywhere on its domain, then we just say that function is continuous. Now, let's think about the meaning of this continuity. Okay, and first of all, the limit of x as x approaches a is just a, right? So this means limit of x as x goes to a is a. And if you substitute this into here, we get limit f of x, x goes to a is equal to f of limit of x as x goes to a. So that means this limiting operation and the application of function f, these two operations are commutative, so they can be swapped if the function is continuous at this point. Okay, so this is what continuity implies. So in a diagrammatic form, we can write like this. So x goes to a by limit, and by application of function, we get f of x. Right? By application of function to a, we get f of a. And by limit operation, f of x approaches f of a. So this diagram commutes. So this is a kind of commutativity between functional application and limiting procedure. Now let's see an example. Suppose we have a function f of x that is defined by this: 0 if x is negative, and 1 if x is positive or 0. Okay, if you plot this function, then it's easy to understand that this is not a continuous function. So if x is negative, then this function is 0. So let's change the color. We have like this. And if x is 0 or positive, then this the value of this function is 1. Okay, and so is this function continuous at x equal to 0? No. Otherwise, it is continuous. Okay, so for example, when x is equal to 1, so, maybe it's not a good example. Let's say it's 2. X equals to 2, then the limit when x equals to goes to 2, then this limit is obviously 2 because it's constant. You know, whether you approach from the left or right, the value of the function is always 1. No, it's not 2, it's 1. So, and the 1 is this value, right? So f of 2. So therefore, this is a continuous at x equal to 2, or you can also try x equal to -3 and you get the same result. And but at x equal to 0, then it's not continuous because the right limit is 1, the left limit is 0. So that means there is no limit at x equal to 0. Otherwise, the right and left limits should match, but it does. They don't match. So we don't have the limit of this function at x equal to 0. Therefore, this is not continuous. And next example, suppose we have this function f of x that is absolute value of x if x is not 0 and equal to -1 if x is equal to 0. So if you plot this function, it looks like this. Okay. So when x is positive, then this is just equal to x. So it's like this. And when x is negative, then it's negative x. So it's like this. When x is equal to 0, it's somewhere here. It's -1. So as you can see, the limit of this function as x approaches 0 is 0, right? So limit of f of x as x goes to 0 is 0, either from the right or the left. They are all 0. But the value of f of x at x equal to 0 is -1, which is this, which is not equal to -1. Therefore, this function is not continuous at x equal to 0. But otherwise, it is continuous. By the way, there is an exception about the continuity of a function when a function is defined on a closed interval. And continuity at these endpoints are defined by either right limit or left limit. For example, in this case, the continuity at x equal to a, a is the lower bound of this interval. So if we have this interval, we cannot approach a from the left because it's not in the domain of this function. So we can approach this point a only from the right. So a from the right. If this is equal to f of a, then we say this function is continuous at x equal to a. And similarly, this upper bound, this point, can be only approached from the left. So when we talk about the continuity of this function at x equal to b, which is the upper bound of the interval domain, then if this equality is satisfied, then we say this function is continuous at x equal to b. Now let's see some properties of continuous functions. Suppose f of x and g of x are continuous at x equal to a. Then their linear combinations are all also continuous. Okay, so k times f of x plus l times g of x is also continuous. And so is their product, f of g, f of x times g of x is also continuous. And their ratio is also continuous, given that g of a is not equal to 0. Okay, so these are all trivial once you understand that the continuity is just defined as a limit, and the limit being the values of these functions at x equal to a. So these are just inherited from the properties of limits. And a similar argument also applies to function compositions. Let's say f of x is continuous at x equal to a, and g of x is continuous at x equal to b, and suppose b is equal to f of a. Okay, then their composite g after x is continuous at x equal to a. So this is also inherited from the property of limit of a function, of functions, or function composition. Continuous functions have many nice properties that makes life easier. And I will list two of these such properties without proofs. Okay, and the first one is called the intermediate value theorem. So intermediate value theorem. Sometimes we call it IVT. And that says the following. Suppose f of x is continuous on an interval, let's say I, that is between a and b. Okay, continuous on an interval means that it's continuous everywhere on this interval. Okay, and also assume that f of a is not equal to f of b. So their values at the endpoints are different. Then, for any value, then the following holds. For any value between f of a and f of b. So the reason why we say between f of a and f of b is that, in some cases f of a is less than f of b, but in other case f of a is greater than f of b. But either case, this L must be somewhere between these two values. Okay, for any value L between these two values, there exists some value C between A and B such that f of C is equal to L. Okay, try to understand what this means. So suppose this situation, let's say we have A here and B here. Okay, we consider this closed interval, and the value of f of A is somewhere here, suppose, let's say, okay, so somewhere here. It's a continuous function. Okay, and the value of f of b is somewhere here. So let's pick any value between f of a and f of b. Okay, let's say somewhere here. Okay, so since the function is continuous, this horizontal line y equal to L must intersect with the graph of this function somewhere. Okay, so that intersect corresponds to this value c. Okay, so if you substitute x equal to c to this function, then L should be, this L should be equal to f of c. So that's what this theorem says. Intuitively, it's understandable, but we don't give the proof. If you're interested, look up Wikipedia, for example. And another important theorem is the extreme value theorem. Let's call it EVT. Okay, this says, again, a function is defined on a closed interval and continuous on that interval on I equals to a between a and b. Okay, if this is continuous and defined on a closed interval, then this function has a minimum value and a maximum value. Well, at least one minimum and one maximum. Okay, so each at least once. Okay, so this is also easy to understand. So let's draw a graph, hypothetical graph of this function, a and b. So this is a continuous function. So it starts from somewhere and ends somewhere. Okay, there are no jumps here. So if you look at this graph, there is always somewhere some value that is the minimum of this function. Okay, so this function cannot take, there's a lower bound here. And since it's continuous, at some point between a and b, the function takes the minimum value. And at some point between a and b, this function takes a maximum value. The maximum can happen multiple times, so does minimum value. But at least we have one maximum and one minimum. Okay, as long as this function is continuous and defined on a closed interval. You know, it cannot be open interval, because in open interval, if it diverges at the endpoints, then there is no maximum, for example, or minimum. Okay. And the continuity plays an important role here. To see that, consider this example. F of x is, let's say, 1 minus x squared. And this is defined on an open interval. Okay, it's not closed. So what does the graph of this function look like? Let's see. So let's see. It's between -1 and +1. Let's say this is -1, then somewhere here is +1. Okay. So when x is between these values, then 1 minus x squared is positive. Okay. And as x goes to +1, this denominator converges to 0. That means this entire function diverges to infinity, positive infinity. And when x is equal to 1 or 0, then this is 1. Okay, so The graph doesn't look very good, but anyway. So it takes values of 1 somewhere here, and it will also diverges to positive infinity as x approaches -1. So this function does have a minimum, but it doesn't have a maximum, right? Because it just diverges. There is no maximum. So it's not continuous on this interval, and it's not closed interval. So all these conditions are important. Continuous on a closed interval. Okay, so that's all for this video. See you later.